I will talk about my work on memorization optimization. This is a joint work with my friend Mohamed Hossein and my supervisor Marco Mondelli. And just to give a brief introduction on something everyone is aware of, training neural networks is a non-convex problem with many disconnected local minima. However, we see that in practice, algorithms like gradient descent can achieve zero training loss. So why is this the case? Well, in a hand-wavy fashion, we can say, yeah, we have many dimensions in these high-dimensional landscapes. So probably gradient descent can find its own way until getting to a global minimum. However, we would want to formally describe this in a less hand-wavy manner. So there is a common recipe to deal with this problem, which is based on the neural tangent kernel. I'm not gonna introduce this object, and for the people that are not very familiar with this, just think about it as an object that describes our network up to the first order of its Taylor expansion. So you can write the Jacobian J of the network, which is n times p matrix. N is the number of samples, and p is the number of parameters. And you can build out of this empirical neural tangent kernel, which is n times n kernel. And again, number of training samples in our model. If we use a quadratic loss, we can write this inequality, which is showing us already something very interesting. The smallest eigenvalue of this kernel can be used to lower bound the gradient of the loss. So we can already see intuitively that there are two things that we can prove to win this game. The first one is that the smallest eigenvalue of the neural tangent kernel is very separated from zero. And it also stays like that as we train our model. In this way, we will be able to provide results in optimization. So to recap, memorization optimization, this is the title of the work, because another result that we have almost for free as we study the smallest eigenvalue of the neural tangent kernel is that for whichever set of n labels, I can find some parameters such that we epsilon interpolate these points. And this follows the corollary of the work on Montanari and Zhang in 2020. The most interesting part is, however, related with optimization, as I was saying, and follows the same line of Ormek and Sultan Kutabi. And the question is, does gradient descent converge to zero loss? And if we can show that, yes, indeed, the smallest eigenvalue is well separated from zero, this is alpha, and the Jacobian doesn't change too much as we train, then we have a geometric guarantee on the decay of the loss. And just to make you understand, this alpha shouldn't be something close to zero. Like, we really want the condition number of this kernel to be as low as possible. So this is the main problem. The main problem is under which settings the neural tangent kernel of a network is well conditioned. And this brings together with it other questions like, okay, is this a function of the activation function or the initializations that we're using? Or maybe the depth, data distribution, or overparameterization. So you can think about it even as a practitioner, like, okay, how should I build my neural network in a way that this condition number is gonna be well behaved? Because this is something that we care if you want to optimize this network. And the last point is the most important, and is about overparameterization. And to give you a very fast pictorial way of why this is the case, of course, if you are working with an underparameterized network, the kernel can be written in this form. And it's pretty easy to see that this is rank deficient. So the smallest eigenvalue of the kernel is going to be zero. So we, of course, want to work in the settings where the network is overparameterized. Because in this case, the matrix is going to be made by this fat Jacobian. And in this case, we might have the situation where the smallest eigenvalue is larger than zero. It's not automatic, but this at least we know that we can do. And the question is, okay, how much should we be overparameterized? And the story is that the more overparameterized you are, the easier becomes the proof. And there is a line of work that progressively pushed down this necessary overparameterization. There is also work that recently achieved tight overparameterization. So as soon as the ratio between the parameters and the number of samples diverges, even very slowly, then we have that the smallest eigenvalue is larger than zero. However, this is done only on a two-layer network. And we would want to do this for deep networks. However, for the deep case, this is a streamline of work that I can show you that push down the width of the network. And as you can see, it's far away from this optimal square root of n. And the last work achieves layers that scale linearly with the number of samples, so number of parameters scales at least quadratically with the number of samples. And why do we want to get to minimal overparameterization? Like why, oh, this is louder. Okay, why do we want to get until this point? Well, I can show you a couple of examples based on two datasets. One is CFAR10, the other one is a subset of ImageNet with this number of samples. We can check how big should be a network that has layers as wide as n, and what is actually enough to fit completely the data points. And for CFAR10, we have this number of parameters. If we work with these wide networks, this is actually what is enough, though. And for ImageNet, it's pretty more fun, because this is more than probably the size of the largest transformer ever published so far. And this is actually the only thing that we need. So it's clear that quadratic is more than we need, and we would want to achieve results in the minimal overparameterization settings, which is what we're doing. So this becomes the last open question, and okay, is the NTK well conditioned for a deep network with minimal possible overparameterization? And I hope I gave you a sense of why this question is very important. And the main technical contribution is, yes, under some assumptions, we can prove this. And the smallest eigenvalue scales as the number of parameters. So it's pretty large and well separates itself from 0. And just to mention, this high probability is with respect to the input data, because we are sampling points from some distribution, and only on the initialization, because I'm initializing my network in a random and pretty standard way. Another thing that I'm using is that the depth of the network is a constant. So when I write these scalings, these asymptotic scalings, I'm not taking into account large L. Okay, so let's dig into the math with a little bit of notation. I'm working with single output, fully connected networks, and the layer widths are going to be indicated with these small n's, with the indices that represent my layer. And again, the depth of the network L is considered as a constant. So there are some mathematical equations that we can write using the chain rule, since the Jacobian is just the derivative with respect to the parameters of the output, which is this. The neural tangent kernel, JJ transpose, can be written as the sum of these partial kernels. These partial kernels are one for each layer in my network. And these partial kernels can be written as this component-wise product, Hadamard product, between this term that represents the features, so basically what we have inside our neurons, and and the backpropagation terms. Backpropagation is a little bit more difficult to explain, but just consider it as this stack of derivatives with respect to every layer up to that point. So again, these subkernels are these component-wise product between the features from the left and the backpropagation terms from the right. I will focus on the penultimate layer, because this penultimate layer is a little bit easier to study, and as I said, I want a lower bound on the smallest eigenvalue of the NTK, but since the NTK is a sum of PSD terms, if I provide a lower bound on the smallest eigenvalue of this last term in this sum, then I'm done, because all the other terms just bring some positive additional terms. If we focus on this very last layer, then what happens? The Jacobian can be written, the rows of the Jacobian, can be written in this Kronecker form, where on the left in blue we have the features, and in right we have the propagation term, which we can write explicitly in this way. These are the neurons up to layer L-2, and this is the propagation term that is written as activation, derivative of the activation times penultimate layer times the neurons at layer L-2. Of course, if we work only on the penultimate layer, to have smallest eigenvalue larger than 0, we need the number of parameters in this matrix, which is n times n, be larger than n. Otherwise, we're screwed, because we wouldn't have a full rank matrix in this penultimate layer. I will give a very fast high-dimensional probability refresher. Hopefully, most of the audience is familiar with these notions. First of all is the sub-Gaussian norm and also sub-exponential norm. What is a sub-Gaussian norm? Sub-Gaussian norm is basically the standard deviation of the smallest Gaussian that can bound the tail of my random variable. And in an analogous way, I can also define the sub-exponential norm, where we're not working with Gaussians but with exponential distributions. We can make the same definitions also for vectors, where we project the vectors on unit norm vectors u beforehand. We can do this even for sub-exponential distribution. And there is one result which is maybe a little less known, which is the Hanson-Wright inequality. This is very important for our proof. We really leverage on this tool, which is that if we have a vector x, which is sub-Gaussian, mean zero with independent entries, then this quadratic form made of this vector will be sub-exponential. And the sub-exponential norm is upper bounded by the sub-Gaussian norm of the vector and the quadratic form we're using to define this big lambda object. Okay, so I told you I want to understand the smallest eigenvalue of a matrix that is defined as this component-wise product between features and backpropagation. The problem is that these two terms, even looked singularly, are pretty complicated. So to get a little bit of intuition, let's work with something way easier. So instead of features and backpropagation, we look at x and y, where the entries of x and y are sub-Gaussian, independent Gaussian random variables. What do we do? Okay, let's look at the rows of this Jacobian, Zi. It's written in this Kronecker form, and I can use a very fast Hanson-Wright inequality to show that the sub-exponential norm of these rows is constant, so it's very small. Other very easy results on concentration of Gaussian vectors would give us that the L2 norm of these rows are very large. So they scale as the product of the number of columns of x and y. And then we use the result of this work by Adam Chuck that says, okay, if there is a very large gap between the L2 norm and the sub-exponential norms of the rows, and this gap scales like the number of rows of the matrix, then we're done. Because ZZ transpose concentrates to the identity matrix times a factor that is exactly the L2 norm of the rows. So in the case where the number of columns of x and y, the product between this number of columns is larger than the number of rows, we're good, we're done. Because the smallest eigenvalue of ZZ transpose concentrates to these nx and y. And this is amazing, because if you look at this is exactly the minimum overparameterization requirement, because the number of columns of x is exactly the width of the penultimate layer, and the number of columns of y is exactly the width of the last layer. So it feels that this strategy and recycling these results from Adam Chuck and this Hanson-Wright style of proof would give us exactly what we want. However, in reality, stuff is more difficult, because first of all, the entries of f and b are not independent, and actually f and b are dependent between each other. So this already makes the story more difficult. And the other thing is that their expectation is non-zero, and this is critical for our proof. And because if we just look at the sub-exponential norm of these non-centered vectors, the sub-exponential norm would be very, very large. So we wouldn't be able to reuse these results. So what can we do about this? First of all, we can work, instead with sub-Gaussian input data, we can work with Lipschitz concentrated random variable, because there is a result, there is a more generalized version of Hanson-Wright inequality that allows us to use these a little bit stricter family than sub-Gaussian, but where we can relax the fact that the entries are independent between each other. And to use this for our feature and backpropagation maps, we would just have to assume that the activation function is smooth. So this is the first assumption we use, that the activation functions are smooth. And what about the centering? This is much more painful, and to get an idea of what we can do about this, we just have to look at what kind of objects we like to use Hanson-Wright inequality. The objects are of this form. Y and x are mean zero, and then we subtract by the quadratic form the expectation of it. So instead of working with this, which is very annoying to me, I would want to work with something like this. So I subtract by the features the expectation, I subtract by the backpropagation part the expectation, and then afterwards I subtract everything from this. So these I define J tilde, which is the centered Jacobian. And of course, I want to provide lower bounds on the smallest eigenvalue of the Jacobian, not on the centered Jacobian. So why this would be beneficial? Well, if we can prove that the original Jacobian is lower bounded in spectrum by this centered Jacobian, then we're done, because we just prove our bounds on J tilde, and then these bounds are going to be meaningful even for J. And this is exactly what we do in a very long proof, but it works, or at least it should. So to recap, what is the sketch of proof? This is the neural tangent. The neural tangent is a sum of PSD terms. And so we can work only on the penultimate layer, which is the easiest for our purpose. This penultimate layer has the rows that can be written in this way, Kronecker form. This form is not Hanson-Wright friendly, so we center it. We show that the thing we want to prove the bounds on is lower bounded by this new object. We prove the concentration bounds on this new object, because now we can do, as I was saying in the easy case scenario. And this gives me a matrix concentration on the centered kernel that exactly scales as the number of parameters in the last layer. So this also gives me the smallest eigenvalue. So to conclude, what did we do? We provide a lower bound on the smallest eigenvalue of the neural tangent kernel for reasonable architectures. So not extremely weirdly overparameterized and deep. We connected this result with optimization, which is very important. And given the line of work I was discussing about trying to push down the necessary overparameterization, we need to have these guarantees. This can be seen as an endpoint, because this is the minimal overparameterization, and I showed you in the pictures. If we go below this point, of course, the smallest eigenvalue is going to be 0. And to mention some possible future works, I just would want to stress the fact that the smallest eigenvalue of this kernel is not related only with optimization, but with many more things. And understanding other layers beside the very last layer, beside being mathematically interesting, could be very insightful for understanding the role of depth in these kernelized models. And an assumption that I didn't mention and is a little bit hidden is that I require my network to not get too wider as I get deeper and deeper. And this we call loose pyramidal topology. And this can be relaxed, but the price to pay is that we would have to use a higher degree of overparameterization. So there is the feeling that there is a trade-off between the shape of the network that we're using and the overparameterization we need to have these guarantees. So this interplay, in my opinion, is extremely interesting. And to conclude, I would want to thank my two co-authors. One is Mohamed Hussein in PFL, and the other one is my advisor, Marco Mondelli. And thank you all for being very focused, hopefully, especially in the first part. And thanks again, and hope to see you around.
Thank you. Do we have any questions? 1 minute.
Thank you. Very interesting talk. And this seems like a very satisfactory result. Can you specify a little bit more? You said that this is an endpoint. So basically, you can show that this is separated from 0, the eigenvalue is separated from 0 whenever it's overparameterized. You don't need any excess overparameterization. And also, what kind of architectures does it work for? Presumably, it also depends on the architecture of the network.
Yes, thanks. I'm working with fully connected, and I'm working with these, as I was saying, these loose pyramidal topologies. So the network does something like these as I get deeper and deeper. So if I need the last layer to be overparameterized, in some sense, I need every layer to be overparameterized. So these can be a little bit restrictive if we consider networks that get wider and wider and straighter, but at least what we see in these very plain convolutional networks or fully connected networks is that indeed the sides get smaller and smaller as we get deeper. So there are not other hidden assumptions. We are working with initializations that are LeCun initialization, so the weights are Gaussian. But I'm pretty sure this is just a way to make the proof easier. We can work even with whichever distribution we like. The important thing is that the standard deviation of these initializations scales like the inverse of the width of the layer that comes exactly before, which is what is done in practice. So again, this should match. And besides these technicalities, I guess there is no hidden weird trick to make this work. So for example, differently from the penultimate work in the line of research I was mentioning, these omega of n was using an initialization that was more artificial. They were really handcrafting the initialization to make this work. In our case, no, we use everything pretty standard.
Thank you.
Thanks.
Any more questions? Hi. I have two questions. The first one is, you neglect all the other layers, and so how loose is the bound? And do you think that most of it is in the last layer, or maybe not?
Very good question. Okay, we also prove an upper bound on the smallest eigenvalue. And if we imagine all the layers to scale with the same width, so let's say square root of n, square root of large n, then the bound is exactly tight, because we show that there is, the smallest eigenvalue is omega of number of parameters, and is also big O of number of parameters. So as I was saying again, I will stress again this loose pyramidal topology. If the network is not constantly wide, then this might not be loose anymore, just because with this informal statement, this number of parameters is larger asymptotically than the number of parameters in the very last layer, because the very last layer is smaller. But in the moment where the last layer is not the smallest anymore, then everything becomes very tight.
Mm-hmm. And my second question is, in order for the NTK regime to be valid, you need assumptions on initialization. The width needs to be very large. In order for you to prove the lower bound, you also made assumptions. And maybe I misunderstood, but I think you said that the width couldn't be too large. So can you comment on whether the assumptions are consistent?
No, okay. The width can be large. Like if the layers are super wide, then we know that neural networks training matches with the NTK learning. And we also know that our results hold for NTK. Like this is, I'm just putting lower bounds on the width of the layers. And now in this setting, I'm proving this with a minimal width that would make this result true in NTK. One thing you can argue is that in this regime, where the layers are only square root of big N, the learning of the neural networks is not well represented by an NTK, a kernelized NTK learning problem. But this is a complete another problem. Like to connect our results with the optimization in real neural networks, we also enforce lazy training. So we do the game of splitting the things in the very last layer and proving that the training is lazy. But if you just look at the smallest eigenvalue problem, then this is consistent with itself, and it's a little bit besides the learning thing.
Thanks.
Thanks.
Yeah, we move next to next speaker.
So basically, you showed that a neural network will, converge well because of this over-parameterization. So we go into a higher dimension, which is somewhat intuitive. When you go to higher dimensions, then you can drive your loss to zero. But then, how good is your convergence point from generalizability? Let's say, for how good it is? Is it okay, when you go in higher dimension, you're going to converge, but how good is your convergence point in higher dimensions?
Okay. Yes, in this work, I didn't mention anything about the relation between the smallest eigenvalue and the generalization or whichever properties. I briefly mentioned in the future works is that this smallest eigenvalue, and generally the spectrum of the NTK, can be related with learning, generalization, even robustness, for example, properties of the network. Intuitively, you can imagine that the condition number stretches your solution. Like if there is a parameter that has associated, if there is a direction in the parameter space that has associated very small eigenvalue, we would have to go in that direction long time to fit in that direction. So this is going against the weight, the L2 regularization, because we're going very far in parameter space, which we can imagine is bad for generalization because we shouldn't explore too far. But there are works that do exactly generalization with these smallest eigenvalue. One is the 2 layers network that I was mentioning from Montanari and Zonk.